Joining us here in person and on Zoom, I'm Megan Doherty, the director of the Museum of the White Mountains. As we gather today, we're all on Indigenous lands. Those of us at the Museum of the White Mountains are on Indakina, which is the ancestral and present homelands of the Abnaki, Pennacook, and Wabnaki peoples. We're grateful for their stewardship of these lands and waterways. For those of you on Zoom, we've put some links in the chat where you can learn more about the Indigenous histories of your place at native-land.ca, as well as more about the Abnaki peoples of Northern New England through the Musée des Abnakis in Quebec. As many of you know, as part of my research for our summer exhibition, I've been learning about efforts to preserve the culturally important brown ash tree, which is under threat from the emerald ash borer. If you couldn't join us on March 7th, when two members of the Ash Protection Collaboration Across Wabnaki Project, or APCAW, were here visiting from Maine, I encourage you to watch the video of their talks, which we'll put in the chat as well. We all learned so much about the work being done to mitigate the impact of emerald ash borer. Tonight, our focus shifts away from the damp valleys that brown ash prefers up into the mountains. For our Mountain Voices series this academic year, we've been exploring topics related to conservation in the White Mountains. Today, we're joined by Georgia Murray, staff scientist with the Appalachian Mountain Club. And before we dive into learning about long-term data collection she's been involved in, I want to share a tiny bit of information about how you can contribute to their research. And given the weekend's forecast, this is a great time to get involved in community snow observation. It's never too late, it turns out, to get involved in community snow observation. So we'll put a link in the chat, and we have some information on the table. There's also some spring ephemerals and information on the table for when that day comes. But there's still a chance to get involved. You just need a ruler and a smartphone to contribute to this really important scientific research on snow, and particularly, I just went to a webinar that Georgia helped organize yesterday on the kind of lack of data in the White Mountains region at a range of elevations. So we have a couple of great data points, but you get higher and there's just not much there. So if you're out hiking, if you live up in the mountains, take a ruler out, measure some snow, and share that data. One data point is, more than they would have had without it. So everyone's welcome and encouraged to join. So with that, I'll turn it over to Georgia, and I'll get this going. Hide these. The hard part is like making it look good in person and there we go. Okay, great. Should be all set now. Thank you, George.
Great. Well, thank you. My name is Georgia Murray. I'm a senior scientist with the Appalachian Mountain Club, and I'm going to speak today about some of the long-term monitoring that we've been doing in the White Mountains around air quality and climate change, and some of the lessons learned over the 4 decades that we've been doing this work. So, for those who are not familiar with the Appalachian Mountain Club, our mission is to foster the protection, enjoyment, and understanding of the outdoors. The research department, which how many people know about the research department? Okay, all right, we've got less than 50% of the audience knows about the research department, but we're a small part of the AMC. We're often known as a trail club or for our facilities in the White Mountains, but research has actually been a part of the AMC since really the beginning, with our founders who were botanists coming up to the White Mountains, but the research department started in the 70s. And we, small group of the staff, provide credible and high quality scientific information and analysis in support of AMC's mission, with a primary focus on natural ecosystems. And the different topics that we study are things like air and water quality, climate change, forest ecosystems, mountain environmental monitoring, which is a lot of what I'll speak to today. And we also do a lot with spatial analysis to understand the lands that we're studying. And we do this with many others at AMC, our policy department and our trails department. And we work across the landscape. The Appalachian Mountain Club has chapters from Maine to Washington, D.C. And we have land in Maine called the Maine Woods Initiative, and we do research there. And we also have a focus in the White Mountain National Forest, which I will talk to today, but also do work along the Appalachian Trail, in the Connecticut River watershed, and different areas across our region. And again, what I'll speak to today is really our air quality and climate change work. And what I want to start with is a success story around a topic that maybe sounds like old news to a lot of you, which is acid rain, an issue that was pretty concerning back in the 70s and 80s. And this just is a graphic showing how the emissions of sulfur dioxide get up into the atmosphere from smokestacks and tailpipes, and then get converted into different compounds and then end up depositing into ecosystems as acid rain or sulfates and nitrates and hydrogen ions. And as they come into ecosystems, they then affect the waterways and even the vegetation and the soils, and can damage ecosystems. And acid rain and acid deposition was really an Eastern United States problem. As we see here, the bright red is the area where there's more sulfate being deposited in 1985. And so it was really the Midwest coal plants that were emitting sulfate or sulfur dioxide that was converted to sulfate. And the winds were really going towards us here in New England. And so we were receiving a lot of this air pollution. Okay, can I move? Okay, so, but I'll start with the end, which is we have a success story under the Clean Air Act with acid rain. So because of amendments to the Clean Air Act in 1990, the acid rain program was developed. And because of that, the emissions of these air pollutants declined dramatically over the next few decades. And you can see the red line, which is the sulfur dioxide, plummeting as we get past 2010. And again, start this and get it to go. Hold on. There it goes. So over time, we see that red, deep red color that we saw earlier in 1985 start to dissipate. So this is the end product. So we saw that the declines in the SO2 emissions, we see the declines in the sulfate being deposited to the ecosystem. So the acid rain program is just one piece of the Clean Air Act. This is a timeline showing the Clean Air Act on the one end, and just some highlights of programs under the Clean Air Act over time that AMC has been engaged on. And you see the 1990 Clean Air Act amendments. We also had Clean Air Act amendments in 1977 that established some of the protections of wilderness areas. Remember, the Wilderness Act was 1964, but because it was already in place and there were already wilderness areas, large national parks and US forest lands, the Clean Air Act came along and recognized these were areas that we really wanted to protect from air pollution. So those amendments went in, and those become important for why we're doing the monitoring we're doing in the White Mountains. Again, the acid rain amendments came in 1990. We had programs like the nitrogen oxides SIP call, which is a state implementation call that required certain states to clean up their emissions from cars because nitrogen oxides contribute to not only acid rain, but ozone pollution, which affects our health. We've had different strengthenings of air quality rules that protect our health as well. One in 1997, and again in 2015 and 2024. The latest one was for fine particulates. And then there's also a program called the Regional Haze Program, which relates back to wilderness protection that recognized that the views were part of what we want to protect in wilderness areas. And because of that, the Regional Haze Program came along and defined how we were going to do that. How are we going to protect wilderness from poor visibility? And there were programs such as the BART rule, which again relates to how this would happen, how this would be implemented. There's transport rules that relate to if New Hampshire can't clean up its own air pollution, we look at other states. And then finally in 2023, they call it the Good Neighbor Rule. All these other acronyms we won't even go over, but it's basically the Good Neighbor Rule under the Clean Air Act, which says basically other states have to be good neighbors and they're required to clean up pollution if they're contributing to another state's pollution. And again, strengthening of air quality rules basically is about public health and ecosystem health. There's certain regulations there that have been improved over time. And most recently, the Clean Car Standards came out today, an improvement of that piece of the Clean Air Act. So you can see there's definitely a lot of different ways that the Clean Air Act works to protect our health and our ecosystems. And this is just a small smattering of those types of programs. And going back to the 1977 Clean Air Act amendments that related to wilderness, in the White Mountains, we have two Class 1 wilderness areas. We have the Great Gulf Wilderness and the Presidential Range Dry River Wilderness. And those are Class 1 areas that require that the White Mountain National Forest, as the land manager, has to monitor and protect those areas, again, around things like visibility, things that relate to air quality. So acid rain, ozone, visibility, fine particulates, and when it gets into the ecosystem, stream water chemistry. And so that relates to some of the monitoring we've been doing. So I don't know if I can get rid of that top bar.
If you click on the more and then click on the high floating media controls, it like automatically pops back up when someone comes.
Okay.
There we go.
All right. I'll know that for the future. So this is a little history bar of AMC's White Mountain monitoring that we've been doing, that I've been involved in. And again, this isn't everything, but it's some of the main pieces. As I mentioned, acid rain was a big issue in the 70s and 80s when our department was forming. And so we began working with a group of scientists in the region, including those at Hubbard Brook Experimental Forest, that were tracking rain chemistry. And there were researchers there that understood that cloud chemistry was also unfortunately very polluted because clouds contain they're like sponges absorbing this air pollution. And so we started monitoring clouds at Lakes of the Clouds, and I'll show some photos of that, how we catch clouds, and found that we were seeing very acidic levels in the early 80s. We also have been involved in monitoring air pollutants that affect our health, ozone, and we were part of a hiker health study that showed that these air pollutants can affect the lung capacity of even healthy hikers hiking on Mount Washington. We monitored fine particulates, again, at Lakes of the Clouds. We've been doing stream monitoring since 1995, and I'll show that data. We were involved in some visibility surveys, looking at the Great Gulf Wilderness area and getting people's opinions of visibility conditions. And also ongoing, we have a plant phenology monitoring program where we're studying the timing of when flowers flower and when fruits form, and that study's ongoing. And we're doing a lot of research around climate trends and indicators in the mountains as well, which I'll talk about more in detail. So again, the monitoring in the national forest was started with a focus around the wilderness areas and tracking these air quality related values. So ozone, sulfur and nitrogen deposition, what we call chronic and episodic acid neutralizing capacity, which I'll explain that, and stream water quality, which is related to that. And so here is a picture of our Lakes of the Clouds monitoring site. That is Lakes of the Clouds hut right there. And this is a little weather station, and that is our cloud catcher. And so it's got a little fin on the back that so it moves with the wind. So it's always facing windward. So it's catching all of the air moving through it, is hitting Teflon strands and depositing the liquid. So as the cloud moves through, it hits those Teflon strands and deposits the liquid form of the cloud, and that's how we catch a cloud. And so we're providing some baseline air quality monitoring that really is very rare in the region. The only other location now catching clouds on the eastern seaboard or eastern United States is at Whiteface Mountain in New York. And let's see, we're just adjacent here at Lakes of the Clouds to the Presidential Range Dry River Wilderness area, and Great Gulf's just a skip and a hop over the summit of Mount Washington. And the monitoring is still done today and had been done under a cooperative agreement with the Forest Service for many, many years. So, and here's an example of our data over time. And so it's these thick bars in the middle are the 50th percentile or the median value over time. And then you can see there's a lot of variability in this cloud water sulfate data. So this is sulfate concentration over time. Each year we collected, and this is the way with cloud chemistry. It is very variable because, as you can imagine, there's so many different steps that goes into when it was emitted over in, say, the Midwest, gets up into the atmosphere, and then travels to us and then is deposited on our cloud catcher. There's, was it cloudy over in the Midwest when it was first emitted? And, how fast did it move across the country to us? And we get this high variability, and this is the same with the whiteface data. So at least we're consistent in how the cloud chemistry looks, is there's a lot of variation, but you can definitely see the trend downward. And that is consistent with other measurements of sulfur in rain chemistry collected at the National Atmospheric Deposition Program sites in Vermont, Hubbard Brook again here in New Hampshire, Underhill, Vermont, and Whiteface, not the summit, but nearby. You can see that we're all seeing the same trend, basically. Yes, indeed, the region is seeing that decline in sulfate as that image showed you in the beginning. Other chemistry is not showing as strong of a downward trend. Here we're looking at cloud ammonium levels. Ammonium is a nitrogen type compound that is really high in concentration in cloud water. It's not as high in rainwater. And that's because of the type of chemistry that we see in clouds. We see both the liquid phase, but also the aerosol phase of sulfate. And that has a lot of ammonium attached to it. And so when it comes in the cloud water, we see high concentrations. And this is because this hasn't been targeted. I should have mentioned in that graph that showed you the declines in the emissions, that was not one of the ones that was showing the strong decline, because this had not been targeted under the Clean Air Act amendments. And a lot of the source of ammonia emissions is agriculture. So it hasn't been addressed like the coal industry has been addressed. So the other monitoring that we've been doing for a number of years is stream monitoring. So, you know, this stuff is up in the air, but eventually it gets deposited into the ecosystems. And it's gonna, you know, come through the watershed, but eventually it's gonna end up in the stream channel. And we can measure what's in the stream channel to get a sense of how is that watershed doing in response to this historical acid rain that it's been experiencing. And it really depends on the soils, but we'll look at a bunch of different watersheds and what's happening. But the important thing to note is that one of the things we're measuring is the ability of the water to neutralize, or really the whole watershed to neutralize incoming acid. So acid neutralizing capacity is just that. It's how well is that ecosystem able to buffer the incoming acidity. And it buffers that by having available calcium and things that are more on the alkaline side to buffer the incoming acidity. And that really depends on the soil types. And unfortunately, we have a lot of granitic soils, and so we don't have a whole lot of buffering capacity to begin with in the White Mountains region. But what this graph is showing is how acid neutralizing capacity, there's my little guy, is related to or affects fish species. So this is acid neutralizing capacity as it's measured is above zero, is much better than below zero, because you can see that once you get below zero, you have no fish, maybe a little fish, but there's definitely this, you know, zone of severe impact to moderate impact as you move up from 0 to 100 in acid neutralizing capacity. And so the Forest Service has developed sort of these thresholds where, you know, streams need to be above a certain acid neutralizing capacity, 25, which is probably right here, in order to not be, you know, considered chronic. And then episodic acid neutralizing capacity is also considered that if you're above 0, they must be above 0, to not be considered episodically acidified. So those were the thresholds that we looked at. Here's just more information about how acidity, acid neutralizing capacity and acidity are very related. They're different measurements. Here we are looking at acidity as pH, probably something that you remember from high school chemistry, that any pH below 7 is acidic, is considered acidic. And different fish, maybe you're familiar with shiners and sculpins, and we get up here to rainbow trout and brown trout, have different tolerances for acidity level. And so if your stream is seeing pHs, you know, in the 5 range, then it's fairly acidic, and certainly acidic down here. So fish are going to be affected. And so that's why we care about acidity in streams, and one of the reasons, and acid neutralizing capacity. So working with the Forest Service again, we set up monitoring sites in Class 1 wilderness areas, the Great Gulf and Presidential Range Dry River, which we've talked about. This is the Great Gulf. To get you oriented, here's Route 16 going up to Berlin. Pinkham Notch is probably in here somewhere. And then this is 302, so Crawford Notch. So this is the Great Gulf Wilderness area, and this is the Dry River. And then there's class 2 wilderness areas as well in the National Forest that came into being later than 1977. Over here, we have the Caribou Speckled Wilderness Area. We have the Wild River Wilderness Area, the Pemigewasset, and the Sandwich Range. And so working with a hydrologist at the White Mountain National Forest, we set up these monitoring sites. The high elevation ones are these right here. Those we had set up early on, but all of these, what we call boundary sites, we started in 2012. So what are we seeing in our stream water chemistry? Well, here's sulfate again, sulfate concentrations through time. And again, for this class 1 wilderness, we started doing some monitoring back in 1995. That's actually before my time at AMC. This is when I started in 2000. This is Rachel Goland. She was really happy she made it to the Great Gulf Wilderness site, which is a pretty far hike. And she's got some samples in her hand. So you can see that sulfate is declining dramatically in the Great Gulf and the Presidential Dry River at these high elevation sites. And this is summer season only. And then when we look at something like organic carbon, we're seeing an increase at both sites in organic carbon. And we'll talk a little bit more about why we think that is. This is the acid neutralizing capacity data across these different wilderness areas. And this is where you start to see, okay, they're not all behaving the same at all. So the minimum acid neutralizing capacity is in red, so the red dots, and then the median level is in blue. So for, one site, you have the minimum and the median, the minimum and the median. And you can see that, the Great Gulf is definitely seeing some very low minimum values and is really, on the cusp here for median values for acid neutralizing capacity. Same with the Dry River, but the Wild River, not doing so bad here. It's, above 25. Blue Brook is a very acidic location. It's surrounded by wetlands. So that has its own unique situation. And then there's, again, these other locations in Sandwich Range and Caribou Speckled and the Pemigewasset. The Pemigewasset looks really good. And the Wanalancet, beautiful spot. If you haven't hiked over there, you got to go. Looks really good. So we have definitely some differences. And as I mentioned before, it's probably related to soils and watershed structure and probably vegetation as well. So there's a number of factors that go into that. But what this does is helps the forest see, where they might have sensitive watersheds versus less sensitive watersheds to long-term acidity over time. So next I'm going to talk a little bit about Dr. Sarah Nelson's research. She's the director of the research department at the AMC. And before that, she was at the University of Maine and has been doing a long study on mountain ponds, largely focused in Maine, but has a recent paper that pulled in ponds from across the Northeast. And she's looking at how mountain ponds can serve as sentinels for how air pollution is changing over time, but also how climate change may be affecting these high elevation watersheds. So, these areas obviously are undisturbed watersheds. That's one of the things that helps us take away a lot of the variabilities that you might see at lower elevations where they're, influenced by land use and things like salting roads, et cetera. And So we're gonna look at the sites across the Northeast that Sarah pulled into the study along with other co-authors to look at the water chemistry. So they found these data sets, whether they were part of studies they were already part of or other studies, and pulled them all together and found 257 ponds to look at, and had criteria around the size of the watersheds or the ponds, and that they had to be above 500 meters, and were sampled between 1978 and 2019. So what they found was similar to what we've been looking at already, is that sulfate also declining in these mountain ponds. The graphs here on my right, hopefully you're right, split up the ponds into the different regions. So the White Mountains are down here, and we're seeing declines in sulfate there across that time frame. But all of these regions are seeing those declines, and 95% of the ponds saw significant declines in sulfate. And here's the Hubbard Brook data again, looking at declines of sulfate deposition over that same time frame. So a 44% decrease in sulfate, so that's a pretty significant decline in that concentration. So at the same time that sulfate was declining, they also, again, split up into these different regions. We're seeing increases in dissolved organic carbon, and similar to the streams data I showed, they're seeing increase in organic carbon in these watersheds. When you see organic carbon in water, it's often brown, and so they call it browning. And 54% of the ponds, we're seeing larger concentrations compared to the lower elevation lakes. So, and they were exceeding a threshold that's been established that indicates that primary production was inhibited relative to, previous time compared to the 2010 onward. So really a significant shift in organic carbon being mobilized. We saw it in streams, we're seeing it in ponds, and to the degree that it's going to shift the biological activity in these ponds. And so her paper wraps up that, there's a lot going on here, but the main takeaway is that mountain ponds are becoming more dilute, and they're seeing increases in DOC. They've seen declines in these pollutants like sulfate and acidity over the 40-year time frame, and that warming, wetter climates produce these really different conditions after we've seen that long-term acidification. So where are we headed from here is the real question, as we bring in all these factors of chemical, physical, and biological, because we're seeing, climate warming after this decline in deposition. So we want to understand where it's headed from here. And there's been some hypotheses based on this work and other that that the climate change piece is part of the driver in this mobilization of organic carbon. And so continued work to do to look at this question. Now I'm going to shift gears again and talk about the climate trends that we've observed in the White Mountains. So we're lucky enough at Pinkham Notch, where my office is right here. And here's the summit of Mount Washington, to have long-term climate records. And that's because in the 30s, when Joe Dodge was the hot manager at Pinkham Notch, he was getting forecasts from Gray Main's weather station, the National Weather Service, but it really wasn't helping him out when he's trying to understand what's happening locally in the White Mountains. And so being a weather geek that he was, he basically worked with the Weather Service to set up some monitoring at Pinkham Notch, started snow depth monitoring and temperature monitoring as part, there's a program within the Weather Service called the Co-op program where cooperative folks establish these sites. And then he was one of the co-founders of the Mount Washington Observatory. And that monitoring began on the summit. And so because of that, we have this great climate record to look at through time. So thank you to Joe Dodge and his friends. And the first time it was looked at was Grant et al. In 2005, looked at the summit record. We then collaborated with the observatory in 2009 to look at both Pinkham and the summit's temperature and snow record. And then I looked at the data again because there had been even more data collected through 2018 in the 2021 paper. And that's what I'm going to talk about now. So here is the record from 1935 to 2018 for the mean temperature at the summit of Mount Washington and at Pinkham Notch. And we're seeing significant increases in temperature at both sites. Certainly you see the difference between, the mean temperatures at the summit are much lower. When we look at it compared to other sites, whether it's, New Hampshire, across New Hampshire or across the Northeast, we're seeing that the summit is a little bit lagging behind, but not too far from the Northeast in degrees per decade. So how much warming are we seeing in degrees per decade? 0.1 at the summit, 0.14 at Pinkham Notch. New Hampshire as a whole is warming faster than that. But we're all seeing warming, but yeah, we're lagging just slightly behind during this time frame. We've added the most recent years and the summit is catching up quickly, unfortunately. And so when we split it out by season, we see even more variance when we look at Pinkham Notch versus the summit, where winter is warming the fastest at Pinkham Notch. And in this data set, it was not statistically warming. So it was spring and fall that were driving the warming that we were seeing on the summit, whereas all seasons are warming at Pinkham. So there's some variation happening with elevation. And so we're trying to understand that difference. But when we looked at the condition of winter by looking at frost days and thaw days, we're seeing that even the summit is experiencing fewer frost days. So these ranges are the summit to Pinkham. So the summit to Pinkham. So 15 to 18 fewer frost days, 12 to 14 more thaw days. Only Pinkham saw fewer snowmaking days before Christmas, but 15 to 33 more growing season days. That's a whole more than a month at Pinkham. The growing season is extended. So both sites are really experiencing these really changing seasons. The seasonality is really shifting. When we look at the snow record at Pinkham, we're seeing a real significant decline in total snowfall, almost 21 centimeters per decade. And then the day of snowmelt is also shifting. This translates into about 2 weeks over this time frame. So really significant shifts in snow conditions and the snow season. So when we put it in percentiles, the maximum snow depth is declined by 50%, the total snowfall by 25%. And again, snowpack is melting out 2 weeks earlier. So the snow season is changing. So you might say, okay, well, we saw that great success story with the Clean Air Act with acid rain. Well, what about climate change and greenhouse gas pollution, which is causing anthropogenic climate change? So let's go back to the Clean Air Act, which is meant to control air pollutants that harm us.
And, again, that was established in 1970. Well, in 1999, there was a petition to EPA to address greenhouse gases because they are air pollutants in the air, causing harm. And it took till 2007 for a Supreme Court decision after a couple battles in the courts for the US Supreme Court to establish that greenhouse gases are air pollutants, which meant that EPA had to take action. And under the Clean Air Act, the next step was to make a determination of what the endangerment was to our health and environment. And so in 2009, there was an endangerment finding by EPA. And because of that, that triggered basically the Clean Air Act process to address the emissions. They found first that it was an air pollutant, second, that it was endangering us and our environment. And so now EPA had the authority to control greenhouse gases. And so in 2010, the tailpipe rule came out, basically reducing the carbon emissions from vehicles. And in 2015, the Clean Power Plan was finalized, but was quickly overturned under the Trump administration, but it did make it to the finish line as being a rule, but it never got implemented. And the 2016, there was an oil and gas methane rule as well. But when the Trump administration came in, that's this upside down situation. Basically, the Trump administration worked to roll back many of these pieces of progress under the Clean Air Act. The tailpipe rule was still moving forward, but they worked to stall that as well. So again, this is not everything that's happening over this time frame, just some highlights. But we're beyond the Trump administration and working with a different administration. And under the 2020, is that right? 22 Inflation Reduction Act, it might have been 23. But anyway, it reinforced this decision here. So this was an important piece to reinforce that under the Clean Air Act, this decision was the right decision, and we're still moving forward to address greenhouse gases under the Clean Air Act. Now, the Clean Air Act is only one tool in the toolbox to address this issue, but it's still an important one because we have this trajectory and we have this tied to historical successes, I think, that we point back to with acid rain. And then just today, the Biden administration released its clean car standards update. So we started back here, and now we're updating, the trajectory of those over time. And it's really significant. And unfortunately, it will get challenged in the courts as much of the Clean Air Act does go through that process. But we feel like the Appalachian Mountain Club is highly supportive of those standards that just came out today, because they are going to shift us towards electric vehicles, which is necessary to get us away from the pollutants, including the greenhouse gases that harm our environment. So other ways that AMC keeps people informed about these issues is our Conservation Action Network, which you can join. This link we can send out later. But that is how we let people know when there's a rule like the Clean Cars rule, for example. Last year, when it was a proposal and the public comment period was open, we sent out an action alert notice to say, please tell EPA what you think about the Clean Cars rule. And of course, gave some bullets about how we thought it was an important rule. And so there's opportunities with the Clean Air Act often to comment on what's happening.
Because the way that the Clean Air Act works is,
when a new administration comes in, they're interpreting the Clean Air Act law that was established by Congress, and then building rules off of that. So there's always a new administration coming in and maybe sort of reinterpreting that law a little differently,
as you might imagine. And so when that happens and when
rules are proposed and put forward, there's always a public comment opportunity.
and that's where AMC gets
Involved quite a bit is in that public comment
opportunity. We obviously
this is our whole AMC Conservation Action Network. So we work on other issues besides climate change and air quality. So I included some of those other issues here as well. We work on protecting mountains and waters and building close to home trail networks and other
opportunities to do things in conservation.
I think community snow was mentioned earlier, but I will mention it again. That is something that we've been working on for the last couple of years now to get people out measuring snow with us. We've got some fans in the audience, so I'm so glad that they were out measuring snow with us this season, and we might have another opportunity this weekend.
But this community snow observation program started out west.
And there's a paper that's out, and I love that the last co-author is community snow observation participants, which is awesome. But it's really about anybody that likes to be out in the snow in the winter time can take a ruler and take a smartphone that has the app on it and contribute to this program. And let's see, I think I have some data in here. So here's an example of snow depth data that's collected at plots and by the USGS through the Maine Snow Survey Project. So these are set stations at different elevations in the White Mountains. And then when we add the CSO data,
you can see that we're filling in the gaps here.
and what I really like to show that related again to a comment that Megan made earlier is that the high elevation CSO sites are catching deeper snow than we would have with the plots. So, you know, now that's not me up at 4,000 feet, but I'm so thankful for the people that are up there making those few observations. So, you know, it really is filling in some gaps for us and bringing in data, especially up at those higher elevations.
We also have a springtime opportunity that relates to our climate change work that's focused on plant phenology. And phenology is basically the timing of when plants and animals seasonally do things
Like budding and flowering or migrating in relation to their environment. And so we're focused on easy to observe forbs that flower across the landscape and relate that to temperature and each spring's unfolding. And we're looking to see how different species respond and whether some species are more responding to spring warming than others. And so this is just an example of
painted trillium, one of my favorites, flowering and then fruiting.
And so you can get involved in this through joining iNaturalist.
And I've included an email address if you want to know more about that program,
Or you can go on iNaturalist and join any of AMC's projects and contribute that way. So iNaturalist is a great fun app to get out this spring with.
So any questions?
Questions in the room, and then I can pull up the chat and we can find where the mouse is. And we can take those as well. Are there questions in the room while I get organized? Oh, that's not. There we go. So thanking you for more information about the cloud catcher. So yeah, any questions for Georgia? Go ahead.
General question, just about how La Nina and El Nino may affect some of the metrics of deposition. If it does, I just noticed there's so much variability in sulfate data earlier on.
Yeah,
And that's what
I haven't actually looked at La Nina or El Nino's.
I guess
Effect.
it's more generally, like
Yeah,
a rainy year, super rainy
Yes.
year versus a
Yes.
drier that is
it
not.
actually would affect, yes,
What I'm reporting there is just concentration, and oftentimes, like at Hubbard Brook, they'll volume weight
their data that
sort of normalizes some of that difference between a really wet year or really, but we haven't really done that analysis with the cloud data yet, but that is something we could look at. But it would affect it, yes, definitely, if it was a really wet or dry year.
Yeah, I was just trying to think because of the extreme weather now, right? Like-
Yeah, that's a good question. We are seeing a lot more extreme,
Weather, I mean, obviously last summer was so wet
Right.
and we collected a lot of clouds.
last summer, so we'll have to look at that in comparison. And we are actually looking at the long-term precipitation record now with our partners at Hubbard Brook, so we'll have to bring those data sets together, take a look. Hey, you got any students? Maybe we could do that.
I have a question.
Yeah.
So I was like, I always want to know something that's like this far beyond what I understand. And I just scheduled these talks so I can keep learning. That's really what it's all about. But my question is about the dissolved organic carbon.
Yes.
And as you were starting to talk, I was like, oh, well, maybe this is a good thing, because that means there's more like food for the fish. I really have like no idea what we're talking about, but that there's like more food for the fish, or there's more, nutrients for aquatic plants, but then I kind of got the sense that maybe this is actually a bad thing, but I couldn't quite,
Yeah.
I wasn't quite sure if
So-
there's like a tipping point with that as well, where we get to, it's like, maybe this is a sign of good, but actually too much is
Yeah.
also bad.
Well, I'll tell you what I know. I think there's pieces that I don't know either, so. But what I do know is that
And why there's that threshold is related to primary productivity is because it is a browning. So it's blocking light, right? So
Okay.
it's changing when we say primary production, we're talking about the algae that are, in there producing.
and so it's gonna change that dynamic.
So that's not a good thing.
Right.
But I think that there's pieces
That we don't know and we need to understand. I know that Sarah is working with some folks that are looking at sort of the life within the pond
Mhm.
to understand that better, especially in relation to
the changing in precipitation, which is also a factor in this.
Right.
So it's the warming of the climate, the warming of the soils too. So there's, this DOC is probably in relation to, not just the warming of the water itself, but the soils are moving, turning over more
Right.
is dissolving and then coming into the pond. And so that's moving carbon away from that. Because we like to think of soils as having a good ratio of like carbon to nitrogen, right?
Right.
And that's a healthy soil. And so if you're starting to move, all of a sudden you're changing that dynamic or that ratio of moving carbon out of the soil, then you wonder, how is that changing the health of the soil?
Right.
And then it's moving into the water and it's browning it, it's, blocking the primary productivity, that's a negative. But I think there are things we don't know that could be, where are we going from here? I think we still need to figure that piece out.
Yeah, and I think there's also, I have this sense that like inorganic things are bad, so that like sulfate's bad, but somehow the organic things were supposed to be good, and then I was like,
Yeah.
wait, I don't think that's what we're seeing.
Well, but
here,
there are
so-
the inorganics that are good are like calcium.
Right.
There's the good inorganics too, so.
Yeah, we've lost a lot of that. So the other thing to think about is that the acidification process was happening over decades and decades. And so soil that produces calcium, it takes thousands of years to make soil. So
Right,
the
right.
timelines are different as to how we're going to recover from this acidification that happened really quick versus replacing that with the important calcium and magnesium. So that's another factor here, is those timelines are off. So I think there's a lot to still figure out. And we are sitting on a lot of data to bring together. So that's Sarah and I are thinking about ways to bring the stream and late data together and see if we can learn even more about these systems.
Yeah. Great. Yeah, you can go
I have
ahead.
two questions. One, really easy. How is day of snow melt defined?
Day of snowmelt.
Zero.
Yes, we have a criteria. So it's basically no snow, or I think it's less than 0.05, like it's like basically no snow. But it has to be that way for 5 days.
Okay,
So like, if it just melted out near you and you get another foot of snow this weekend, then it's not day of snow melt. Because it
but if
hasn't
it
been.
happened like.
If it happened, yeah, if there's been 5 days, then we kind of look, see, that's the whole thing, is this criteria was based on what we knew before. Now we're in this very variable system. Maybe we have to think about our criteria again, because, the data is there to go back and look at and apply different criteria. So, in our paper, we say this is the criteria we used. And so that's how our day of snow melt is.
Yeah, and I think it totally makes sense for people.
Yeah.
But there is that we're thinking about, like, when is the first day of snow melt after snow actually? Right? Like,
Right.
And then how many of those?
Right.
we have?
Yeah,
Right.
That's a good point.
Like,
Yeah.
winter, this winter.
Yep.
My second question was whether you were monitoring in your water chemistry samples, you've been monitoring aluminum. Fluoride.
Yes. So aluminum and what?
Fluoride.
Fluoride recently. Because Ralph Perrin, yeah, he has a fluoride problem. Not at work, but yeah, so I don't think the lab, so we basically send our samples to the Forest Service lab that does Hubbardbrook samples.
Center.
Yeah, it's in Durham. So we do have aluminum data. And so we've looked at that as well, because aluminum mobilization is an issue that we're concerned about when we have a lot of acidity. So the hydrogen ions come in and they bump off the easy ones first. So they bump off they're a +1. So they're going to bump off potassium, because that's a +1. But if there's more acidity coming in, then it bumps off the +2s, which is like the calciums and the magnesiums. When it's really acidic, they bump off the aluminum from the soil, which is a +3 or +2 or +3, depending on the pH. But that is when you're in a really acidic situation, is when you're mobilizing aluminum, and aluminum is toxic to both roots, fish. So that's a really acidic situation. So we do have that data, and we look at aluminum mobilization across our stream sites. Fluoride I haven't looked at. I know we have a little bit of that data.
We looked at it for a brook trout project because it's for the two. The counter and DOC as well. It's
Yeah.
like potential buffering, it like binds
Yes.
skills and prevents the aluminum. So even if you have high fluoride, I think it's insane.
Okay.
There's like.
Yeah, and you see the relationship between DOC and aluminum. So, yeah, interesting.
Well, thanks. Thanks For those of you joining us on Zoom, those of you here in person, thanks for making the drive, because you came around, not over the lake route, not the mountain route. And yeah, thank you all for joining us. And for those of you, I know some of you are already members and support the museum. If not, I hope you'll consider joining us, and your support makes programs like this and our exhibitions possible and allows us to bring, I feel like there's this podcast I like, and she says, invite smart people and ask them stupid questions. And I feel like that, you know, if it's a, you know, or just ask them all the questions, right? Just ask every question, and you know, and to bring smart people and ask them questions that don't make sense to you, and everyone learns more. And so thank you for joining us and helping me understand what dissolved organic carbon is doing in all of these lakes and ponds and streams and everything else. So thanks so much, and thank you all for joining us.
Thank you.
Thank you.